Hey everybody, welcome back to Quantitative Reasoning, and today we're in section 6.3 and we're going to be looking at applications of linear equations. So last time in section 6.2 we solved several linear equations together, and this time in 6.3 we're going to be using those solving skills to solve some word problems, and we're also going to talk about how to solve a formula for a given variable. So let's get started. So before we just jump in and start solving problems, let's kind of get a little strategy here, because word problems are something that a lot of people kind of pause at and they're not sure how to proceed, and that's because everyone's different, so you can't really memorize your way through them. They appear in all different kinds of forms, so you have to learn how to approach them instead of just memorizing steps. But here is a general strategy that we can use to approach any word problem. So step 1, read the problem carefully several times. Don't skip over that. Read the problem carefully several times until you can state in your own words what values are given and what values the problem is asking you to find. A lot of times you read a word problem, and it happens to me too. You read a word problem and at first it just seems all confusing. There's so much information, your brain can't sort it all out right away. And I think that leads to a feeling of being lost, and that's uncomfortable. So a lot of people they want to shut down and say, oh, well, I can't do word problems, they're always hard. No, you can do word problems. Word problems are what links math to the real world, so you can do it. So the key is, if you read a word problem and you're not initially clear on what they're asking, read it again. Sometimes you have to read it several times. But when you can finally state in your own words what values they're giving you and what values you're looking for, that's when you're ready to move on. At that point, you are going to assign a variable name to the unknown quantity in the problem. Sometimes there's more than one unknown quantity, but at least you're going to give some kind of name to the value that you're trying to find. So that'll be at least one unknown quantity. The variable can be X. Depending on the problem, you might want to use a different letter, but it doesn't matter what letter you use as long as you know what that letter means. So you just give the unknown quantity that you're looking for a variable name. Now, if there are other unknown quantities as well, then you might have to give them names too and write a little expression for each one of them in terms of X. In other words, write a little equation for that new variable that uses the first variable you named. And then you'll want to put the whole thing together in one equation that models the whole problem. And you might start off with an equation that has several unknowns in it, but that's where you'll substitute in your little expressions from step 2. And what you want to end up with is one equation that only has one variable, and then you can solve that one equation for that one variable. At that point, you can take that value and use it to answer the problem's questions, or whatever they're asking you. You might have to plug back into another little expression that you wrote, or whatever pops out might be the actual answer you're looking for. But you'll just always want to make sure that you are answering whatever question the problem is asking you. And then the last thing you want to do before you consider the problem finished is take your solution that you found and check it in the original wording of the problem. Now, don't check it in the equation that you wrote, because there might be a mistake in your equation. But go back to the original wording and plug in your answer there and see if that answer makes sense in the context of the problem, and then you can be sure that you've done it correctly, and then you can move on. So let's look at some common phrases that are used in word problems to represent each of these mathematical operations. So usually to indicate addition, you'll see a word like sum or more than or increased by. And then to represent subtraction, you'll see words like minus, decreased by, subtracted from, difference, less than, or fewer than. For multiplication, you'll see things like times, product, 2/3. So not 2/3 specifically, but any fraction. So 2/3 is just here to represent all the fractions. 75%. So again, the number is not what's important, but if they use a percent symbol, there's probably going to be multiplication involved. Multiplied by, of course, means multiplication is involved. Twice. So twice just means 2 times. So we already have the word times here. So if you see the word twice, that probably means multiplication is involved in the relationship somehow. And then for division, the words divided by, of course, quotient, or reciprocal, those all represent division. Okay, let's look at an example. So this is example 1, and it says the median yearly before-tax income of a full-time worker with a bachelor's degree exceeds that of a full-time worker with an associate's degree by $15,000. The median yearly before-tax income of a full-time worker with a master's degree exceeds that of a full-time worker with an associate's degree by $30,000. Combined, 3 full-time workers with each of these educational attainments earn $195,000 before taxes. Find the median yearly before-tax income of full-time workers with each of these levels of education. So step 1 of our strategy says go back to the problem and read it again and pull out the important information. Make sure that you can identify what the problem is telling you and what the problem is asking you to find. So usually what they're asking you to find is at the end, of course. So it says find the median yearly before-tax income of full-time workers with each of these levels of education. Which levels of education? Well, the ones that were mentioned in the problem. So let's go back. They talked about a full-time worker with a bachelor's degree, a full-time worker with an associate's degree, and a full-time worker with a master's degree. So we are responsible for finding the median yearly before-tax income of a worker with an associate's degree, a bachelor's degree, and a master's degree. So what I'm going to say is I'm going to let A represent the median yearly before-tax income for an associate's degree. B is going to be the median yearly before-tax income for the bachelor's degree, and then M will be the median yearly before-tax income for the master's degree. Now, I don't know if you might have already noticed this, but this problem is really wordy. So what I would like us to do is kind of simplify it a little bit. Notice that all the way through the problem, everywhere they talk about someone's income, they don't just call it income, they call it the median yearly before-tax income. And yes, that is the value that we're dealing with. You can see on this chart they've broken income out into before-tax and after-tax income. So yeah, they're asking us and they're talking to us about the before-tax part, and it's a median value as opposed to an average value or a maximum value or something like that. But we don't have to differentiate between those things because the problem only ever refers to median yearly before-tax income. So what I'm going to do is I'm just going to go through and get rid of everywhere that it uses the words median yearly before tax, and we'll just think of that as income. Okay, so that we're just simplifying things a little bit. And then they don't ever talk about just a worker, but they talk about a full-time worker. Well, we don't ever have to differentiate between a full-time and a part-time worker because that's just not part of the problem. So go ahead and get rid of the words full-time, everywhere you see the word full-time. And now let's look at it again. So the income of a worker with a bachelor's degree, that's represented by the variable B, exceeds that of a worker with an associate's degree by $15,000. Okay, so they're saying that the income of the worker with the bachelor's degree exceeds that of the worker with the associate's degree by $15,000. So the word exceeds makes you think of which math operation: add, subtract, multiply, or divide. So of course it's addition. because the worker with the bachelor's degree makes $15,000 more than the worker with the associate's degree. So it takes the associate's degree plus $15,000 to equal the amount for the bachelor's degree. So let's try to write that down. Oh, and another thing, notice that every time they use a dollar amount, it's always thousand, thousand, thousand. So we're not going to write those thousands, we're just going to keep the number. And then all of our answers will come out in thousands automatically without us having to write a whole bunch of zeros. So I'm going to write that the salary for the worker with the bachelor's degree is equal to the salary for the associate's degree worker plus $15,000. And that's what this highlighted part right here says, isn't it? The bachelor's degree exceeds that of the associate's degree by $15,000. Okay, let's go on to the next bit of information. So it says the income for a worker with a master's degree exceeds the income for the worker with the associate's degree by $30,000. Okay, this time the master's degree is $30,000 more than the associate's degree. So I'm going to write master's degree equals the associate's degree plus $30,000. Okay, so far we have two equations. And then they gave us one more piece of information. They said combined, 3 workers with each of these educational attainments earn $195,000 before taxes. So what that tells us is the associate's degree worker plus the bachelor's degree worker plus the master's degree worker, together their incomes all add up to $195,000. Okay, now we have a good equation here, but we have too many variables. This equation has 3 different variables in it, and I only need to work with one variable at a time. So at this point, what we need to do is go back to our first 2 relationships and see if we can replace the B and the M with the information that we have here. So the A is fine. The B can be replaced by A plus 15. And then the M can be replaced by A plus 30 because M equals A plus 30. And so now A plus B plus M is 195. So A plus this expression is 195. Okay, now the parentheses really aren't doing anything here because there's nothing to distribute, so I can just lose the parentheses. And now we can combine like terms. Here on the left side of the equal mark, we have A plus A plus A, and so that's 3A. And also on the left side of the equal mark, we have 15 plus 30, so that's 45, and that's equal to 195. Now to solve this for A, you know what to do. We need to isolate the 3A terms, so we need to eliminate the 45. So we'll put minus 45 on both sides. And that will leave us with 3A on the left side of the equal mark. And on the right side, 195 minus 45 is 150. So now we've worked it down to here. And we want to isolate the A, so we divide both sides by 3. And that will leave us with A equals 50. Now you remember, of course, that all of our numbers represent not just dollars, but thousands of dollars. It was $15,000 here and $30,000 here. So right here where we have found A equals 50, that 50 really represents $50,000. And of course that was one of the values that we were asked to find, but we've also got to find the median yearly before tax income for the bachelor's degree worker and the master's degree worker. So now let's take our 50 and plug it into this little relationship that we wrote for B. So the bachelor's degree worker's income is the associate's degree worker's plus 15,000. So B is 50 plus 15, so that's going to be 65. So of course that represents 65,000. And the same thing for the master's degree worker. M equals A plus 30 becomes M equals 50 plus 30, so that's 80, and that represents $80,000. And so now what we want to do is take these 3 numbers that we found and go back to our problem and see if they fit in the problem, just to, kind of check our reasoning. So remember that they said a bachelor's degree worker's income exceeds an associate degree worker by $15,000. Is that true? Does the bachelor's degree exceed the associate's degree by $15,000? And that is true. Okay, now let's go to the next piece of information. It says the master's degree exceeds the associate's degree by $30,000. Okay, is that true? The master's degree amount was $80,000, the associate's was $50,000. So yes, the master's degree does exceed the associate's by $30,000. So it looks like it's pretty good here, and then if you add all three of these together, of course you'll come up with $195,000, so that matches this last piece of information. And now I want you to notice that even though they gave us a graph here, we actually did not use the graph at all to solve the problem, did we? So what does that tell you? That tells you that when you see a graph, you don't need to panic about it. Don't let that make you freeze. Just read the problem and write down what you know one piece at a time, and that's how you solve a word problem. So here is another example, and this is example 2. And really the only way to get good at solving word problems is to do a lot of word problems. It takes practice, and I would even tell you do the same word problem several different times so you can really get it in your head what's happening here. So let's read this one together. It says the figure shows that the first year class of 2018 was less interested in developing a philosophy of life than the first year class of 1969 had been. In 1969, 85% of the first year class considered this objective essential or very important. Since then, this percentage has decreased by approximately 0.8 each year. If this trend continues, by which year will only 25% of first-year college students consider developing a meaningful philosophy of life essential or very important? And so this is another example where all the information that we need to solve the problem is right here in the problem description, and the graph is really just here as an illustration, but I do think it's worthwhile to look at it, and that might help you understand what they're asking us a little better. So the title of the graph is Life Objectives of First-Year College Students, 1969 to 2018. And on the y-axis, we've got percentage calling this objective essential or very important. So in 1969, 42% said that being well off financially was essential or very important. But 85% said that developing a meaningful philosophy of life was essential or very important. And you can see that by 2018, when they asked college freshmen this same question, only 47% said that developing a meaningful philosophy of life was essential or very important. So that's a significant drop. And what they're telling us in the problem is that this percentage has decreased by approximately 0.8 each year. And then they ask us if the trend continues, by what year will only 25% of first-year college students consider developing a meaningful philosophy of life essential or very important? Okay, so when we look at the problem, this is an important piece of information. The percentage has decreased by approximately 0.8 each year. So what we can do is use this piece of information to write a little formula, but we need to assign a couple of variable names. So basically, the percentage drops off or decreases by 0.8 for each year. So we need a name for the percentage, and we need a name for the number of years that have passed since 1969. So let's let the variable d represent the percent. So this will be the percent of first-year college students who believe that developing a meaningful philosophy of life is essential or very important. And then let's just let the variable x represent the number of years since 1969. So notice that in 1969, 85% of the first-year class considered this objective essential or very important. So we're starting at 85%, and we are decreasing the percent by 0.8 for each year. So our formula would be that d equals 85 minus 0.8 for each year. So you can see that when it was 1970, it would only be 1 year since 1969, and so the percentage would have been 85 minus 0.8 times 1. And then the next year, it would have been 2 years since, so it would be 85 minus 0.8 times 2. So that's how we're going to make it drop 0.8 each year. So now, if we look at the question, by which year will only 25% of first-year college students consider that essential or very important? So they're giving us the value of D, and they're asking us to find the year. But what we're really going to find here is the number of years since 1969. So I'll go ahead and plug in 25 for D. So I'll have 25 equals 85 minus 0.8 times X. So we want to solve this for X. And remember, it's going to tell us when D is 25, how many years since 1969 it will have been. So we'll start solving here by isolating this X term. So we'll subtract 85 from both sides. That will leave us with negative 60 on the left, because 25 minus 85 is negative 60. And then on the right, all we will have left is negative 0.8x. And now to isolate the variable, we'll divide both sides by negative 0.8. And so now we have negative 60 divided by negative 0.8, and that is 75. So what we just found out is that by the time the percentage is down to 25%, it will be 75 years since 1969. So what year will it be? Well, if we take 1969 and we add 75 years, then that's going to be the year 2044. So let's see if this makes sense. Now go back to the original problem, and if we start in 1969 with 85% saying that developing a meaningful philosophy of life is important or essential, then it drops by 0.8 each year, and it's been 75 years. So 0.8 times 75 would give us 60, and then 85 minus 60 would give us 25%. So it does make sense that after 75 years, only 25% would still hold this opinion. Okay, here's another one. You drive up to a toll plaza and find booths with attendants where you can pay the toll by cash or credit card. With this option, the toll is $5 each time you cross the bridge. The attendant gives you the option of buying a barcoded decal for $25. With the decal, you get 25% off the normal toll of $5 for each crossing. Find the number of times you would need to cross the bridge for the costs of the two options to be the same. Okay, so our strategy here is going to be to write a little expression that will let us calculate the cost of crossing the bridge if we have to pay $5 every time. And then we'll write another expression to calculate the cost of crossing the bridge where we get 25% off the $5 each time, but we have to pay $25 up front. So in both of these cases, the number of times we cross the bridge is what determines the total cost. So let's let X represent the number of bridge crossings. Now, without the decal, if we're just paying for each individual trip, it costs $5 each time we cross the bridge. So under that deal, the amount that we would pay total is 5 times however many times we cross the bridge. But with the decal, we'll get 25% off the normal toll crossing, which is $5, okay, but we're going to get a 25% discount. So let's go ahead and calculate that discount. The 25% discount would be 25% of $5, and so that's $1.25. Every time we cross the bridge, we save $1.25 off of that $5 fee. So if it's $5 and we save $1.25, then we're paying $3.75 for every crossing. So with the decal, our cost would be the $25 that we have to pay up front plus $3.75 for every time we cross the bridge. So now the problem asked us to find the number of times we would need to cross the bridge for the two costs to be the same. So what we need to find out is where does 5x equal 25 plus 3.75 times x? This is where the cost of the two options is the same, so we just have to find out how many crossings that is. So we will start solving this for x. Now notice I have an x term on the left and I have a constant and an x term on the right. So if I want to eliminate this x term, I'm going to have to subtract 3.75x from both sides. That will leave 1.25x on the left equals 25 on the right. Now divide both sides by 1.25 and we will find out that x equals 20. So we would have to cross the bridge 20 times in order to break even for buying that 25% off decal. But after that 20th crossing, then the decal would start to save us money. Now we could check our work here if we wanted to. So if we take the 20 and we plug it into each expression, they both should give us the same amount of money. So 5 times 20 trips would mean a total cost of $100 without the decal, and then with the decal, 25 plus 3.75 times 20 trips would give us a total cost of $100 as well. And so we were correct. 20 trips is where you break even. Okay, here's a retail example. After a 30% price reduction, you purchase a new laptop for $840. What was the laptop's price before the reduction? So basically, we want to find the original price of the laptop. So that's what I'm going to assign a variable name to. I'm going to call it P. So P is the original price of the laptop. Now, we know that it cost $840 after a 30% price reduction. So how can we calculate the discount, the 30% off of the original price? So the discount is 30% of the original price, or 30% of P. Now of is assigned to multiply. So percent of means we're going to multiply. Now we're going to talk about this a lot more in another section, but anytime you want to do a calculation where you've got a percent symbol, you've got to convert that percent into decimal form. So 30% is 30 hundredths, or we would write that as 0.30. So 30% of P is going to be calculated as 30% times P, and so that's our discount. And now we know that a final price is always an original price minus the discount. So if the final price was $840, that means that $840 is equal to the original price P, so we'll put P, minus the discount, and that's 0.30 times P. Okay, now we want to combine like terms. So this is 1P, right? 1P minus 0.3p would leave 0.7p. 1 minus 0.3 is 0.7. And so now you see that we've got this little equation here, and all we need to do is divide both sides by 0.7 in order to isolate p. So the 0.7's divide out, and we're left with p equals 840 divided by 0.7, which is $1,200. Okay, so it looks like the original price of the laptop was $1,200. Now let's just check our work and make sure that it makes sense. So if we did this correctly, then 1,200 minus 30% of 1,200 should give us 840. So let's try it. 1,200 minus 30% of 1,200, and you can type that in your calculator, and you will get $840. So we did it right. Okay, now we're going to switch gears a little bit and talk about how to solve a formula for a different variable. So far, every equation we have solved has only had one variable, but formulas contain two or more variables because there's always at least one thing that you're plugging in and another thing that you're trying to calculate. So solving a formula for a variable means rewriting the formula so that the variable is isolated on one side of the equation. It does not mean obtaining a numerical value for that variable. You're not trying to solve and get a number, you're just trying to isolate a different variable. So to solve a formula for one of its variables, what you're going to do is treat that variable as if it were the only variable in the equation. Think of all the other variables as if they were numbers. Whatever variable you're trying to solve for, first isolate all the terms with that variable on one side of the equal mark and all the terms without that variable on the other side of the equal mark. And when you've done that, then you can divide both sides by the same non-zero quantity, that'll be the coefficient. So you'll divide both sides by the coefficient of that variable to get that specified variable alone. And that's how you solve a formula for a variable. Let's practice on that together. So here we have a formula. This happens to be the formula for the surface area of a cylinder, but that doesn't really matter. You don't have to know what the formula is for. But the formula is A equals 2 pi r squared plus 2 pi r h, and they're asking us to solve for h. In other words, we want to isolate the h. So what I'm going to do first is copy the formula down a little bigger so I can work on it. Okay, now I want to isolate this h. So that means first I need to isolate this term. So that means this term that does not have an h, this needs to go to the other side of the equal mark. Now there's already an a over here. So if I subtract 2 pi r squared from both sides, notice that these cannot be combined because they're not like terms. So they're still going to be separate terms. I'm going to put the a first because it's positive. So it's going to be a minus 2 pi r squared for the left side of the equal mark. Over here on the right, these two terms add up to 0, and all that's left on the right side of the equal mark is 2 pi r h. Okay, now I've got the h term isolated, and I want to eliminate all of these coefficients. So if I treat all of this as one number, like for example, if this said 3h, you would just divide both sides by 3, right? So that's what we're going to do here. I want to eliminate this coefficient 2 pi r. So I'm going to divide that side by 2 pi r. That means I need to divide the whole other side by 2 pi r. And now the 2 and the pi and the r all divide out, and that leaves the h isolated on this side of the equal mark. So h equals all of this. H equals a minus 2 pi r squared, all divided by 2 pi r. Now I think your next question is probably going to be, do we need to simplify this? Like, should we cancel out the 2's, the pi's? Should we cancel out one of these r's with this one? And the answer is no, we cannot do that because 2 pi r is not a factor of the top. 2 and pi and r are all parts of this term. They're all factors of this term, but they are not a factor of the entire numerator, so they can't be reduced. And so we'll just leave it in that form. Okay, here is another example, and it says, the total price of an article purchased on a monthly deferred payment plan is described by the following formula. T equals D plus PM. In this formula, T is the total price, D is the down payment, P is the monthly payment, and M is the number of months one pays. Solve the formula for P. So, it really doesn't matter what all of these variables represent if it's not a formula that we're going to try to use. It's kind of interesting to know what all these variables stand for, but it's not necessary in order for us to solve the formula for P. So let's just go ahead and copy down the formula the way they gave it to us. Now remember, we're trying to isolate the P. So that means we need to start by isolating the term that contains P. And that means that this D term needs to move to the other side of the equal mark. So we need to eliminate it from the right side. So I will put minus D on the right, but that means I have to put minus D on the left. And now when I look at the left side, these will not combine. So I'm going to have t minus d for the left side of the equation, and then my equal mark, and then pm on the right side, because you see d minus d will add up to 0, so that disappears from the right side. Okay, now still trying to isolate the p is being multiplied by m. So what's the opposite of multiplication? And that's division. So I need to divide by m on the right side. That means I need to divide by m on the left side. And so that's going to divide out the m's on the right, and that will leave me with p equals all of this. It's on the left side right now, but if I start with p equals, then on the right side I'll have t minus d all over m. And that's it. So I hope that you'll go to the homework now and get some practice. And anybody can do this with a little practice, so spend a little time working on it and practicing. And if you have any questions, reach out to your instructor. Otherwise, I'll see you guys in the next section. Bye.